Hi, and welcome to this look at a question linking observations to what direction the position of equilibrium might be shifting in. It's from the 2018 OCR Unified Chemistry paper, question 2C. So it gives you a description of cobalt-2 and what it does with water ligands and with chloride ligands. And it means the blue cobalt-2 chloride complex formed would be COCl4 2-. So from your transition metals chemistry, you can see it's quite similar to the structure of CuCl4 2-, which is in the OCR textbooks. So this is slightly applied because it's just taking you outside the normal version, which is copper, or cobalt version. But cobalt and copper are both in the 3D subshell section of the periodic table, so they're going to form similar types of chloride complexes, that is tetrahedral. Now it also tells you which colors they are: pink for the cobalt hexa aqua, which is this one here, and blue for your cobalt chloride, cobalt tetrachloride 2-. It then gives you a description of what the student does, and it asks you to write the equilibrium equation for the reaction that takes place when the color of the solution changes. So there's two versions here. You can either just say what happens in experiment 1 or what happens in experiment 2, because in the question there it says when the color of the solution changes. That could be pink to blue, or it could be blue to pink. So you've got two possibilities. This is the pink to blue, and this is the blue to pink. So you can write it either way around. So if you have a quill look, you can see that the reactants in experiment 1 are the same as the products in experiment 2. So it's just the same equation, really, just going back and forth. So there's your highlighters there to show you the colors of the various reactants and products involved. So I'm going to go for what the mark scheme had. In the mark scheme, it allowed you to do it the other way around if you wanted to. So I'm just going to go with that particular one. Now what's interesting is it's got H+, isn't it? So don't forget those ions, like I did. I forgot to put them in, didn't I? So you've got to be a little bit careful here. I didn't put them in actually because I was just putting 4Cl-. So if you don't put in the 4H+, you need to make sure you just put in 4Cl- on the left-hand side there. So that obviously refers to experiment 1, because this is the pink and this is the blue. And this goes from pink to blue. So taking that particular version of it, adding HCl increases the concentration of Cl- ions, these ones here. So therefore the position of equilibrium, we're going to shift to the right to use these up according to the Chatelier's principle, producing more blue cobalt chloride complex. This occurs at high temperatures because it says so there in the question. So that must mean that that particular position of equilibrium shift is endothermic. So having a look at the mark scheme, you can see there's two options. And also you'll see that there's some allows on the right-hand side in the guidance. What that means is there's some flexibility because they're focusing on certain things they're testing here, and other things they're a bit more flexible about. So for example, they're not going to be too precious about how you actually write out COCl4. So normally when we teach this, we encourage students to write it out with square brackets, but it allows two different versions there. You can see up here, there's two possible ways in which you could write the equation. And for the equilibrium shift, there's different types of wording that they're going to allow as well. Now, what you're going to make sure is that the direction of shift you're talking about represents what you're describing from your equation. So the two things have to match up and make logical sense. The enthalpy change is definitely going to be endothermic, so it's the only correct answer there. Okay then, again, thanks for listening. Until next time, see you soon.